Hello, my name is Kai and welcome to the Theoretical YouTube channel, where about 4 years ago I made this video. And boy howdy do I regret it. Well, no, I don't actually regret it. It was actually a really fun video to make and a really interesting problem to solve. The only problem is that it's all wrong, or rather just a gross oversimplification of the mechanics at play. But that was 4 years ago, and you know what you can get with 4 years and thousands of dollars? A degree in mechanical engineering, physics, and applied mathematics, where you learn all about vibrations, material properties, and of course, heat transfer. And if I've learned anything, it's that I knew nothing when I made that video back in high school. But now, I'm smarter, stronger, I know what a Nusselt number is, and how to read this. I feed off of adiabatic processes. My best friend is a calculator, and 75% of my vocabulary is comprised of the letter K. So today I wanted to redeem myself. With my new understanding of how heat transfer works, I wanted to tackle another problem. Not the turkey one again, I already did that. Instead, I thought I'd take a look at the legendary battle that happens thousands of times every year between the mighty sun and the lowly snowman. But to give them a fighting chance, we're not just gonna pit the sun against one snowman. No, today we answer the question, who would win, the sun or 1 trillion snowmen? The sun. It's not even a competition. Even with 1 trillion snowmen, which sounds like a lot and is a lot of snowmen, it's still nothing in comparison to the gargantuan size of the sun. Even if the snowmen weren't so easy to melt, there's just nothing on our comparatively small human scale that 1 trillion of could do to compete with the sun. Like in the original meme, who would win, 1 trillion lions or the sun? It was a funny question to pose, but there was pretty much no real debate online. There's just nothing 1 trillion lions could do to get the upper hand against the sun, unless they attacked at night, of course, that would work. To wrap our minds around how big these numbers we're dealing with are, let's put into perspective how many snowmen 1 trillion really is. If you were able to build 1 snowman every second, then it would take you 11.5 days to build 1 million snowmen. But it would take you 31.5 years to build 1 billion. And then it would take you 32,000 years just to build the trillion snowmen. That is a massive number of snowmen. If you were to lay all of those snowmen out in a grid across America, each one could be no further than 3 meters away from each other. If you were to pile them into just a big mountain, it would rival the size of Mount Everest. And that's big, but it's not that big when we compare it to the yellow dwarf at the center of our solar system. Because while Mount Everest is big, it's not that big when compared to the entire Himalayan mountain range. And the Himalayas aren't that big compared to an entire continent. And an entire continent isn't that big when compared to the whole Earth. And even Earth isn't that big when compared to the other planets, and even the biggest planet in the solar system, Jupiter, isn't very large when compared to the sun. Our sun, which isn't even that big of a star by the way, is 1.41 times 10 to the 27 cubic meters in volume. That's 1.4 billion cubic meters. And it's dense too. 1.4 times as dense as water on average, weighing an astounding 1.98 times 10 to the 30 kilograms. Here's the craziest comparison I found to really make this number sink in. The sun has more kilograms than there are atoms in 280 human bodies. If each of your atoms weighed 500 pounds, you still wouldn't weigh as much as the sun. So the sun wins, hands down. There's just nothing 1 trillion snowmen could do to remotely affect it. There are really only 2 ways to kill a star, the tactical approach and the blow it up approach. The tactical approach involves poisoning it with copious amounts of iron. Because stars are essentially just massive fusion reactors, They get all their power from smashing atoms into each other and creating new atoms, and in the process, releasing a lot of energy. Which works up into a point. Hydrogen atoms combine together to get helium atoms combine together with each other or other hydrogen atoms to get either lithium or beryllium, and so on, and it goes up the periodic table until you get to iron. You see, iron is just such a stable element, so when you try to smash two of them together, you actually take more energy than you release, which means they don't really work for a fusion reactor. So rather than fusing, iron just sits there in the star as it just creates more and more of this useless mass until it reaches a breaking point. A star is only a stable structure so long as the fusion reactions create enough pressure on the inside to balance out the gravitational forces trying to pull it all towards its center. Without fusion, the star's gravity would take over and it would collapse in on itself. And that is exactly what happens when a star makes too much iron, because the iron can't be used as fuel for the fusion processes, but it still contributes to the gravitational forces. So once a majority of the star's core is made of iron, it runs out of fuel and implodes. And by the way, it's during that implosion that so much energy is released that the iron is finally able to combine with other elements to create the entire periodic table in the subsequent supernova. So the tactical approach to killing a star is to pump it with so much iron that it can't do enough fusion to balance out its own gravity, so it collapses and explodes. But this would require a ridiculous amount of iron, like more than the mass of the sun in iron, and we've already been over how absurdly big the sun is. Also, needless to say, our snowmen don't really have any iron to begin with, so that's kind of off the table in general. The second approach to killing a star is to just blow it up. By this, I mean to just hit it with so much energy that it destroys any structure it had and scatters all of its components across the galaxy. But how much energy could that really be? It's a lot of energy. But we have a lot of snowmen. It's not enough snowmen. But what if we got them going really fast? They couldn't go fast enough. But what if they were each a nuclear bomb? Even if that were so, you'd need billions of times the number of snowmen we already have. Really? Yeah, the amount of energy it takes to completely blow something apart that's being held together by gravity is called the gravitational binding energy, and it's represented by this formula. The sun's gravitational binding energy is really big, like bigger than I could make a comparison to. And it's all thanks to this guy right here. That, my friends, is the square of the object's mass. And the object, the sun, is already the biggest number we've come across today. And when you square a really big number, you get a really big number. We have 1 trillion snowmen. That's a 1 with 12 zeros after it. But this number has 60 zeros after it. That's 3.96 trillion. Thankfully, it's multiplied by this really small number and divided by this reasonably large number, but it still comes out to 2.28 times 10 to the 41 joules of energy. It would be nearly impossible to deliver that much energy using our snowmen, and here's why. You know Einstein's famous equation, E equals mc squared? It's one of the most brilliant formulas in all of physics because of how groundbreaking it is, and yet how simple it seems. One of Einstein's greatest discoveries is called mass-energy equivalence, which basically states that mass and energy are essentially different forms of the same thing, and that given the right conditions, one can be turned into the other. And the ratio you get when you turn one into the other is that 1 kilogram of mass is worth c squared, or 8.988 times 10 to the 16 joules of energy. Now, that's a lot of energy, and we have a lot of mass to turn into that energy. But how close can we actually get to the energy required to blow up the sun? I'm gonna say we have some pretty big snowmen to give them a chance. So let's estimate they each have about 2 cubic meters of volume, and they're made of some decently packed snow. So after some calculations, we find that they weigh about 1,000 kilograms, or 1 metric ton each. And we have 1 trillion of them, so 1 trillion snowmen, each weighing 1 ton, is 1 trillion tons of mass. Now, plugging 1 trillion tons, or 1 quadrillion kilograms, into E equals mc squared, we find that if we were somehow able to convert all of our snowmen into pure energy, that the maximum amount of energy we could get out of them is 8.988 times 10 to the 31 joules. Hey, that's pretty close, right? We need 10 to the 41, and we have 10 to the 31. That's only like 10 to the 10 off, right? No, you cannot just subtract those exponents like that. We have a very small fraction of the amount of energy we need. In fact, when you do the math correctly, you find that we don't even have 1/2 of 1/10,000,000th of 1% of the amount of energy it takes to blow up the sun. If you were able to bombard the sun with snowmen that turn into pure energy like a nuclear bomb on impact, then you would need over 2 sextillion of them. That's more than 6 times the mass of Mercury. Now, technically it would be possible to just deliver the energy it takes to blow up the sun using our snowmen if we got them going really fast. And I'll spare you the details, but by rearranging this equation and plugging all of the numbers we have, you'd find that we need our snowmen to be moving at 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999% the speed of light. Not to mention, we'd still have to generate all of that energy to somehow get them moving that fast. So whether you're trying to poison it with iron or just blow it up, there's really nothing short of a black hole that could do that much damage to the sun. That is, unless we don't have to destroy the sun. After all, we know that eventually it's going to run out of fuel and die in about 5 billion years, while our snowmen just have to sit far away enough and watch. So I'd argue the real question here is, how close do the snowmen have to sit to the sun to not melt after 5 billion years? Now, to figure this out, we need to understand a few different concepts. 2 of them are easy, and 2 of them might need a little bit more explaining. First, luminosity. That is the amount of energy the sun gives off as light every second. Right now, the sun's luminosity is about 3.83 times 10 to the 26 watts, but that number will change over billions of years as the sun grows from a yellow dwarf to a red giant. Next, albedo. This is the amount of light that an object reflects rather than absorbing. A perfectly white object might have an albedo of 1, meaning it reflects 100% of the light that hits it, so it would never heat up from being left in the sun. This is why white cars stay cooler than black cars. Black surfaces generally have an albedo close to 0, which means they absorb a lot of the light that hits them and heat up from it. Now, we also need to understand something called a view factor. A view factor is essentially the fraction of light that leaves one surface and ends up hitting another surface. Let's take a look at an example of 2 circles centered on the same spot. If we choose a point on the inside circle, it should seem obvious that no matter what direction a light ray may leave that point, it's going to hit the outside circle. And this is true for all points on the inner circle, meaning the view factor from circle 1 to circle 2 is 100%. However, let's look at a point on the outside circle. Some of these rays of light coming off that point will hit the inner circle, but some of them will miss it entirely and go right back to the outer circle. For this reason, the view factor from circle 2 to circle 1 is less than 100%, and exactly how much depends on the size of the 2 circles. In this case, we can find the view factor using this formula, but that formula looks different depending on the scenario. In our case, we'll assume the snowmen are all squeezed into this giant sphere, with this giant sphere being the sun. That makes this our view factor. Now, the final concept you need to understand is something called black body radiation. You know how things sometimes glow when they get really hot, like metal, fire, or, the sun? Well, technically everything is always glowing, no matter how hot it is. The reason we can see things glowing when they pass about 800 degrees Fahrenheit is because they're emitting a lot more light that we can actually see. In other words, they're emitting more of the visible spectrum. But that doesn't mean that cooler things aren't also emitting light. Our eyes just can't see the light that they are emitting. For instance, humans and other things about our temperature are constantly emitting infrared light, which is why night vision cameras are able to see them like they're glowing, because they are. Now, a black body is something that absorbs all incoming radiation and reflects none of it. In other words, its albedo is 0. A consequence of this property is that the amount of radiation a black body emits is a direct result of its temperature, following this equation. So, a black body that's exactly 100 degrees Celsius will emit exactly 1099.4 watts for every square meter of exposed surface. But not everything is a black body. In fact, most things emit only a fraction of the radiation a pure black body would. And that fraction is called the emissivity of the object. And when we multiply the theoretical black body radiation of a surface by the emissivity of that surface, we get the actual amount of light that's emitted. So a non-black body that's still 100 degrees Celsius with an emissivity of 0.5 will emit exactly 459.7 watts for every square meter of exposed surface. In our case, snow has an emissivity of about 0.9. And that's all you really need to know in order to solve this problem. The luminosity gives you the amount of light that's coming from the sun, the view factor tells you how much of that light actually hits the snowmen, the albedo is how much of that light is reflected into space, and the black body radiation is how much light the snowmen just radiate to naturally cool themselves down. So now that I explained everything and set the whole problem up, you could just do it yourself. It'd be a much more rewarding experience, and you might even learn something that I couldn't explain. No? Still want me to... Yeah, okay, figures. First, let's start by defining all of our variables, and it's a lot, so I'm not going to bother writing them on the board or even saying them to camera. I'm just going to read directly off the script. 1 trillion snowmen is about 2 trillion cubic meters. A sphere with a volume of 2 trillion cubic meters has a radius of about 6,300 meters. Wow, that's really big. With a density of about half that of water, 1 trillion snowmen weigh about 1 trillion tons. We already calculated that one. The sun has a radius of about 696 million meters and has a current luminosity of about 3.83 times 10 to the 26 watts. Wow, that's a lot of light. Our 12-kilometer wide snowball has an albedo of about 0.98 and a emissivity of about 0.9 and a maximum temperature of 0 degrees Celsius. With a radius of 6,300 meters, its total surface area is 4.99 times 10 to the 8 square meters, but that's really only being heated from one side, and any heat loss due to the radiation from the back won't have nearly enough time to propagate to the front, evidenced by the radiative BO number of 841, which needs to be under 0.1 to ignore spatial effects within the ball. I didn't explain BO numbers, but just know that the front is going to get hot a lot faster than the back. For this reason, I'm going to make the effective surface area equal to half the total surface area, or 2.5 times 10 to the 8 square meters, which means the object will decrease in temperature over time, but the front of it will never dip below freezing, which is what we really care about. Finally, I'm just going to assume the snowball starts at the same distance Earth is for the sun for simplicity, then we can solve for the minimum distance the ball can approach later. Now let's calculate the amount of light that's absorbed by the snowmen from the sun. For this, we essentially just take the amount of light being emitted from the sun and decrease it twice. First, using view factor, and second, using albedo. Using this equation, we find the view factor from the sun to a 12.6 kilometer snowball 150 million kilometers away is about 9.11 times 10 to the negative 15. This is barely anything, but it makes sense. Out of all of the light rays coming off of the sun, this is the fraction that happened to hit this relatively tiny snowball more than 100 billion meters away. Then multiplying the 3.83 times 10 to the 26 watts of light coming off the sun by this view factor, we find that only 3.49 times 10 to the 12 watts end up hitting our snowball. Most of that doesn't even get absorbed. With an albedo of 0.98, 98% of the light just bounces off, and only 2% is actually absorbed. Multiplying our previous number by 0.02, we get that only 6.98 times 10 to the 10 joules of energy are absorbed every second. And that's a lot of energy to absorb every second, but let's compare it to how much energy is being released by the snowmen due to blackbody radiation. Using this equation we saw before, called the Stefan-Boltzmann law, a black body at exactly 0 degrees Celsius should emit exactly 314.94 watts for every square meter of exposed snowman. But we don't have a perfect black body, so we multiply this number by the emissivity of 0.9 to get 283.9 watts per square meter, and then multiply by the effective surface area to get 7.06 times 10 to the 10 joules of energy emitted every second. So with 7.06 times 10 to the 10 joules being emitted and only 6.98 times 10 to the 10 joules being absorbed, if our giant snowball were stationed in orbit around Earth, the front surface would not melt, but rather it would actually cool down as it loses 884 million joules of heat energy every second. But how close could the snowmen actually get before they start melting? By subtracting the amount of energy being emitted from the amount of energy being absorbed, you can make one big mega equation for the amount of energy gained or lost depending on how we change the variables on this right side. For instance, in our current setup, the net heat gain is negative, but if we were to place the snowball only 1 million kilometers away from the sun, then the heat gain would be positive. And if we set the heat gain to exactly 0, then we can solve for the closest distance the snowmen could be before they started to melt. The actual solving for D is left as an exercise to the viewer, but I found this equation for the minimum distance, which puts the snowball no closer than 32.79 million kilometers away, which is actually way closer than I thought. I mean, that's closer than Mercury. But I used the same equation to find what temperature Mercury should be with its own radius, distance, albedo, emissivity, and it looks like it all checks out. So, is that it then? Our snowmen can just hang out around Mercury for 5 billion years until the sun dies? Not quite. Remember, the sun won't just stay as a yellow dwarf for 5 billion years and then suddenly die. As it ages and starts to fuse heavier and heavier elements together, it's going to expand into something called a red giant. And when it does, it will reach a maximum radius of about 200 times its current size, or 139 million kilometers. And its luminosity will surge to 2,000 times its current value, or 7.69 times 10 to the 29 watts. At this point, the sun will fully engulf Mercury, Venus, and maybe even Earth. Needless to say, the snowmen are gonna have to hang out a bit further. And now it's really easy to figure out exactly how far that is. Since we already put everything into one big equation, to solve the problem with these new parameters, we just have to multiply the size by 200 and the luminosity by 2000. And if we do that, we get that the snowman would have to sit at just about 1,468,119,200 kilometers from the sun, or just a bit further than Saturn. At this distance, the sun will never produce enough energy to actually melt the snowmen. In fact, they'll cool off to about -43 degrees Celsius, even at the sun's biggest and brightest, just before it collapses and dies. Well, technically the sun won't die in the same way other stars will. Our sun is actually a pretty small star, and because it's so small, it's never gonna actually explode into a supernova when it dies. When it collapses under its gravity, it just won't explode. Instead, it'll become an extremely dense, extremely pressurized rock. And it's so pressurized that the matter it's made out of doesn't obey normal laws of physics. It's crazy. It's something called a black dwarf, which is really cool, but ultimately a topic for another day. For now, you can like this video if you did, and subscribe if you don't want to miss my mathy holiday-themed video next year. Or this year, depending on what year this comes out. It's probably 2025 already. I procrastinated this a lot. And hey, if you actually hate math and science and you prefer literary analysis of pop culture, then you're in luck. That's actually what this channel is primarily for. I just come on here and hijack it every once in a while to talk about physics and stuff. But it looks like that's all I've got for you today. So as always, thanks for watching, and I'll see you later.
The sun is a deadly laser.